Good morning, everyone, and welcome once again to another session of the JKMRC Friday Seminar Series. So before we begin, on behalf of the University of Queensland and the Sustainable Minerals Institute, we'd first like to acknowledge the traditional owners of the land on which the university sits, the Turrbal and Jagera people, and pay respects to their ancestors and descendants who continue cultural and spiritual connections to country. So it's my great pleasure today to welcome Simon Michaux. So Simon is an Associate Professor of Geometallurgy at the Geological Survey of Finland in the Circular Economy Solutions Unit. He has a Bachelor of Applied Science degree in Physics and Geology from Queensland University of Technology, as well as a PhD in Mining Engineering from here at the University of Queensland. He has 18 years of experience working in the Australian mining industry in research and development, 12 months at Ausenco in the private sector, as well as 3 years in Belgium at the University of Liège, researching circular economy and industrial recycling. His recent work experience in Finland at the Geological Survey has been in the development and transformation of the circular economy into a more practical system that is able to navigate the twin challenges of the scarcity of technology minerals, as well as transitioning away from fossil fuels. The title of his talk today is "The Green Transition Will Not Work as Planned. What Might We Do Instead?" Please join me in welcoming Simon.
Hello, everyone. So I'm going to give an update of where my work has gotten to in the last couple of years. The green transition will not go as planned, but what might we do instead? Okay, that's good. So the summary, where we're going for the next little while. I'm going to give an update of the work that's been done since I've presented last a year ago. New developments, there's been quite a bit of response on social media. So I've actually taken that critique and actually sort of developed new work. How big should the buffer for the management of wind and solar intermittent supply actually be? Can pumped hydro deliver the needed power storage buffer? Can stored hydrogen deliver this buffer? And one of the scenarios that has now been suggested is, can a 3 times build out of wind and solar plus a 6-hour buffer plus a 90% reduction of cars resolve the resource shortfall, scenario N? Then I did a sensitivity analysis, and we'll finish up with some proposed solution vectors. So, status of the work, where have we gone? What I've done is I've actually gone to some targets set by the IEA in a prediction for the net zero by 2050. And by 2050, these are tables 3.2 and 3.4. In 2050, they've made some predictions about where they think things should be. And we're looking at renewable energy will have taken over. Share in total generation will be 88%. The transport fleet will be entirely electric vehicles or hydrogen fuel cells. Aviation will be synthetic fuels and biofuels. Shipping will be a combination of ammonia, hydrogen, and bioenergy. So I've taken these predictions and I've actually said, all right, if we are going to hit that target in 26 years and a few weeks' time, what would that look like? Okay, so here's a quick systems map of the work that's been done. I mapped the system as it is now, oil, gas, and coal, what has actually been done, what happened in the calendar year of 2018, what actually happened. I mapped the transport fleet, what actually happened, and I also looked at if each of these transport fleet was actually turned into an electric vehicle or a hydrogen fuel cell or with biofuels or with ammonia, what would actually be needed to actually produce all that or supply all that. And then from there, well, we need to generate that electrical power. And then I looked at a number of power stations. Now, what I also looked at was for wind and solar are highly intermittent. They actually need a buffer. I've now got 4 calculations for 4 different buffer sizes based on references in the literature. My calculations so far have been based on 28 days. That turns out to be too conservative. We'll get to that in a moment. From there, we now actually have the needed amount of power, 48,909.2 terawatt hours of annual electrical power generation in addition to what we have now. And then I looked at actually sort of the number of units and the metal required to make those units. And so I went through this process here. So we need 65.19 terawatt hours of batteries. And this is the amount of hydrogen we need to produce. And I went through a series of, well, how many units do we actually need? What's the installed capacity? And for things like batteries, I looked at a range of different battery chemistries based on the market as it will be in 2040, again, from an IEA prediction. And that came down to a total quantity of metals required to phase out fossil fuels. That was then put up against mineral reserves, mineral resources, and mineral resources under the sea. The baseline calculation went something like this. 1.4 billion vehicles traveled 16 trillion kilometers in the calendar year 2018. Now, in 2021, about 1% of the transport fleet was electric vehicle. And only in 2022, 6.7% of the global energy, primary energy pie was renewable power generation. So that means the non-fossil fuel system as it is at the moment has yet to be constructed. And as it's yet to be constructed, it can't be recycled. So this is a mining story. So this was to actually look at is, can the mining industry deliver? So these are the tasks. Electric vehicles, fleet 1.39 billion vehicles, we have to charge those vehicles, and we need that amount of power on an annual basis. We're going to produce hydrogen as a direct fuel. We're going to produce steel in a hydrogen atmosphere. We will produce ammonia via hydrogen. And we're going to phase out existing fossil fuel power generation. And we're going to heat buildings with the latest generation of heat pumps, all of which require electricity. And that's all been summed together for 48,909.2 terawatt hours. Now, the numbers have gone up because a lot of my critics and people who are reviewing the current work going through peer review have requested extra things be added to the calculation. Everyone's got a hobby horse, and demands have been made to actually include things, but that means the power bill goes up. We're also going to make biofuels. Now, according to the IEA, 37% of the maritime shipping fleet will be on biofuels. And the aviation industry will shrink by 38%, and that will be on biofuels. To do that, we need 940 million tonnes of biofeedstock. To put this in context, the wheat crop in the same year was 402 million tonnes, less than half. Right, so this task is enormous. And so we had the needed number of power. I actually looked at the actual power metrics actually sort of supplied in 2018 about what was actually delivered, did some statistics, worked out what the metrics of the average size power plant would be and what they delivered. And I worked out that we will need 796,210 power stations of average size, or an installed capacity of 29.9 gigawatts of installed power across a range of different systems. And that brings us to the buffer. So the size of the buffer for wind and solar, which I'll talk about shortly, there's now 4 calculations. So 6 hours, which has come from the University of Princeton, and this is what the establishment thinking actually is at the moment, 5 to 7 hours. 48 hours, 28 days, which is what I picked as a fairly conservative estimate. 12 weeks is probably the closest value of what we actually need. Now, this paper actually came up with that figure by looking at when we have bad weather spells where wind and solar actually don't work very well, you often have more than one. Like you have like a period of bad weather, and then a couple of days later you have another period, and then another period, and another period. And so the grid then has to recover from that and build up the buffer again. And it needs 12 weeks to actually sort of get through that. Then when you also look at solar radiance, that 12 weeks number does actually line up. So what I've done, instead of actually sort of saying one buffer is what's needed, I've done 4 parallel calculations. What is the metal required for each of the different metals across each of the different 4 systems, assuming a buffer? The buffer turns out to be the largest task, and that's how we got these numbers here. Where's the metal going? So this is assuming a 28-day buffer. Now, we'll go through this in a moment about what's actually appropriate here, but 28 days is actually quite conservative. The vast bulk of the metal, this is copper, the graph is copper. The vast bulk of the metal is going into the 28-day stationary storage battery bank. Now, what this means is, and it's not viable, until we actually resolve the ability to deliver or deliver a buffer, wind and solar power generation are not viable as the primary energy system in the next industrial era. Now, that's a tough thing to say, but that's where we're at. Now, we'll go through some other options later, but that's where we're at. Until we resolve that, we can't use wind and solar, or we have to put up with variable power supply, which will cook our electronics. So electronics will have to evolve, one of the two. So putting all this against the mining production rate, this is the mining industry producing in 2019. I picked 2019 because this was the last year before COVID, and in 2020 we had all these supply disruptions, and we've got these weird artifacts in the data. So what we've got is in this column here is the global mining production in 2019 across all the metals, and each column is the years to produce the metal we require based on that table I showed earlier at the same rates of 2019. Like how many, if this capacity remained the same, how many years production will we need? For 6 hours, 48 hours, 28 days, and 12 weeks, the whole system with that buffer. Anything more than 27 years is coloured red because we need to get this done by 2050. So what we're seeing here is all four buffers are showing the mining industry in its current form will not be in a position to actually produce the needed amount of metal, and multiple metals are a problem. Here are the numbers graphically. The black is mining production. This is a log scale too. So the pink is the 6 hour buffer, the whole system with a 6 hour buffer. The yellow is a whole system with a 48 hour buffer plus 10%. The red is the whole system plus a 28-day buffer. And the blue is the whole system plus a 12-week buffer. Now, it's to be remembered, this is for the first generation of units. Wind turbines, solar panels, what have you, they all wear out. And is it 10 years, is it 20 years, whatever it is, when they all wear out, they've got to be decommissioned and reproduced. And that'll put pressure on recycling. But one way or another, we need to find this volume of metal and we go again. So now, let's put this up against the needed number of mineral reserves. So we have the four different systems, from 6 hours out to 12 weeks. The hatched column on the left for each of these metals, copper, nickel, lithium, cobalt, graphite, and vanadium, is up against reported reserves. So the amount of metal that we need up against existing reported reserves as they were in 2022. Right, not enough. Remember, the real answer is somewhere around the blue. So, all right, let's include mineral resources. Now, a reserve is associated with, say, a feasibility study, usually a pre-feas, some sort of economic signature that these resources can be extracted. A resource is a patch of mineralized ground where the mineralization is a little bit above background. It includes things that are really, really low grade. It includes things that are at a depth that we can't reach. And it includes things that are at a mineral grain size that we can't grind to. So just because we have a resource doesn't necessarily mean we can actually get to it. But mineral reserves plus resources are also not enough. Remember, we need to get to the blue. Now, that comes to one of the ideas that I've come across, which is one of the most flamboyantly stupid ideas I've heard in a long time, and that's to mine the sea floor. Chinese are already doing it. So let's look at it. Would it even work? This is what we need up against mineral reserves plus mineral resources on land plus the undersea resources that we know of. Now, of course, we've only mapped a tiny section of the seafloor, and there must be more down there. But the metal that we know of at the moment in the system we call planet Earth, up against between red and the blue, not enough. Remember, this is to produce the same number of units that we had in 2018, 5 years ago, just to stand still. And in 20 years later, we go through it all again. This is the same numbers as this graph, but it's on a linear scale. That's a log scale. And you can sort of think, oh, it's not that different. Here it is in a linear scale. So now the reserves are the grey, resources are the white, and under C is the black. Nowhere near enough. So when the fail is so strong, one facepalm is not enough. How did we get here? For the last 50 years, we've been using ideology to solve our problems without checking the numbers against reality. That's the simple answer. And it's been a policy across multiple sectors. So how big should this reserve actually be? Well, this is Princeton University's the Net Zero America project. It's quite a nice project, and they've actually sort of made a prediction about how big the buffer should be. What they've done is they've done a simulation across a number of days and the day-night cycle, where during the day we use more power and during the night there's less power. And the solid line is demand low. This is the demand. And so sometimes supply exceeds demand, and sometimes it's the other way around. So what is happening here is when supply exceeds demand, they capture it and they store it for a couple of days and they release it when there's a shortfall in the peaks. And so what they're doing here is the day-to-day difference in balancing. Our electronic technology needs sinusoidally clean power at the same frequency, same current, and same voltage in a very narrow efficiency peak. Any variation in that at all, and we get brownouts and power blackouts and power spikes. So what they're looking at here is the day-to-day balancing, and in this case, they only need a couple of hours, 5 to 7 hours. What they have not done is look at the long-term variation. For example, the difference between summer and winter. In summer, the sun is not as strong as the sun is in summer. So let's look at that. Right, so here is the solar radiance in Berlin for the year of 2015. And you might notice in summer, the sun is somewhat stronger. Now, the IEA would have us has a prediction that wind and solar together will now take the lion's share. So this chart, let's say this chart now represents 38% of the global energy mix, and it has to be stable. These systems are so large that we now actually have to have them internally self-sufficient, and they cannot be balanced off against something else. So if it's to be stable power, pick the halfway mark. So that halfway mark is the dotted line. Anything over that dotted line will have to be captured and stored. And anything under that dotted line will need power to be released from somewhere else, a power buffer. So the power buffer is that grey area. And as you can sort of see, 6 months of the year, we're going to need access to that buffer. So the power buffer would need to actually store power for about 6 months, collect power for over about 6 months, store it for 6 months, and then release it slowly over several months after that. That's 28 days. So 28 days in context of solar power is not enough. It's too conservative. There's 48 hours, and that little red line strip there is 6 hours. 6 hours is not enough. 6 hours will not balance this system, not even close. It's not even a single night. So what's happened here is the planning, the engineering behind the planning for renewable energy systems have completely dropped the ball and missed this simple problem. It turns out we don't have the technology to store such a lot of power for such a long time. This is a case study of a concentrated solar power system in Spain. It's actually part of a network of gas and coal as well. And so, but if it was a standalone system, it would look something like this. Now, they looked at 2 months, June, summer, and November in winter. The dark orange is what would be power that would have to come from the power storage. So for the month of November on its own would require 16.2 days of buffer capacity, and they would have to store it for 4 to 6 months. Right, 16.2 days for a system in Spain where the sun shines pretty well. Right, so that's solar. Wind. So wind is highly variable. This is a wind meterage in the UK for a couple of months over a period of time. Look at the variation of this. Again, this chart would represent 38% of the global energy mix, and it would have to be smoothed out. So the UK Parliament did a study in 2014. They found that the wind production was so erratic it could not be predicted. It didn't help they were hit with some unseasonal storms, but that happens. Right, so the variations were a problem. That line there is 6 hours. It's about 6 hours. The resolution of the graph wouldn't allow me to actually make a smaller bump, but 6 hours is not enough to balance and smooth out that chart. The buffer is substantially more than establishment thinking would actually sort of accept. The United States Department of Energy picked up my work in 2021. They found that my ideas were quite different to what they were actually expecting based on how they've been advised. So they did an audit across the year 2022-2023, and they did an audit on their largest power system that they had in their administration, 100 million people, the PJM RTO network. What they found was that wind and solar did indeed underperform for many months of the year. And not only were capacity factors low, but they were low at the worst possible times. Winter is when we need to chew up more power to heat homes, but that's when solar is performing the worst. The numbers I collected at the time from the Global Energy Observatory determined what power stations actually delivered and what was their actual availability in terms of operating hours across the year. Solar PV units produced power 11.4% of the time, and wind was producing 24.9%. Now, wind we could probably improve up to about 33% with engineering, some engineering advancements. However, wind and solar now actually are demonstrated that these assets will be idle most of the time, simply because they're subject to the weather, and there's not a lot we can do about that. This is what we have to work with. Remember, I am not suggesting that we don't use these systems, because they're all we have at the moment, and fossil fuels are going. But this is what we have to work with, and it won't go the way we think it go. The system will be somewhat smaller than we actually are planning for. So now there's the question of, can we actually get this buffer power storage some other way? Most power storage at the moment is done with what's called pumped hydro storage. 99% of it is actually pumped hydro at the moment. Pumped hydro is when you have a hydroelectric system on a river, and then above that river in an elevated position is a second reservoir of water. During the night, water is pumped up the hill into the reservoir, and during the day, when it's on peak, the water flows back down the hill, generating electricity. So the question is, can pumped hydro be expanded to reach our storage needs? The ANU did a study, and they've had 530,000 potential sites worldwide. And you might notice very few of them are in Northern Europe, but all right. When I first started to look at this with some of the researchers in the European Commission, they very quickly told me that it's be politically unacceptable to rezone such a large amount of land that's already under development. But if this is what we have to do, then let's look at it. The question became as follows: how much fresh water would be tied up in pumped hydro storage? Most of these sites are not next to the coast. They're all inland. So we are talking about fresh water. So we take the 28-day buffer, which is too small. We need to deliver 2,192 terawatt hours for the year. Given a flow of 100 cubic meters of water per second through a generator, and say over a head of, say, 570 meters, like that's the drop it goes through, we're going to deliver a power of about 500 megawatts. So 500 megawatt hours will need 360,000 cubic meters of water. Assuming an 81% efficiency, we will need 1,949 cubic kilometers of fresh water. Now, here's where it gets interesting. In 2018, the annual water withdrawal from the hydrological cycle on the planetary scale was 3,990 cubic kilometres. So these are the numbers graphically. This is the water that we extracted in 2018, where agriculture took most of the water, and the blue is industry. The pink is the extra water we would need on top of that to deliver the buffer if pumped hydro was what we were actually using. Now, if we are looking at something between the 28-day and the 12 weeks, we are looking at a substantial increase of fresh water over and above what we are taking now. Now, at the moment, in this, as each year passes, we're taking more and more water from the environment. We're not going to be able to do an extra 48% on top of that. It's just not practical. So pumped hydro cannot deliver such a large amount of power storage. Right, so what about hydrogen? Hydrogen storage is actually often looked at too. So once we have a kilogram of hydrogen, if we put it through a PEM cell, it can deliver 15 kilowatt hours per kilogram. So a kilogram of hydrogen, 15 kilowatts. But to make that hydrogen, if we're not going to use natural gas, we need about 50 kilowatt hours a kilogram to produce that hydrogen. Now, when I actually did this study at the time, PEM cells were running about 55 kilowatt hours. I think they're down to about 52 now. So 50 kilowatt hours is actually conservative. And I've done that to reflect efficiency gains to make the study more valuable for longer. Once you've got that hydrogen, you've got to compress it into a 700 bar storage tank. And that's about 2.5 kilowatt hours a kilogram. So for every kilogram of hydrogen, you need 52.5 kilowatt hours. So that's a round trip of 28%. Now, for power storage, 80% is the low end of what's acceptable. But let's say we went for it anyway. So down here we have, here is our 4 levels of power buffer, 6 hours out to 12 weeks. This is the electrical power that has to be stored and delivered back to the grid. There's substantial numbers. And then we went through to actually produce this hydrogen. This actually shows the increase of power generation to make that hydrogen over and above the 48,909 terawatt hours. Down at 28 days and 12 weeks is between 27 and 81% over and above and atop of the existing system that would have to expand to make that hydrogen and deliver that power buffer. Now, because wind and solar represent most of our power generation, some of that power would also have to be further supported again. So what this is showing is we don't have the technology to produce such a large amount of hydrogen, store it and transport it. Storing hydrogen is tricky. So hydrogen, while it has its place, is not our primary energy storage. So pumped hydro can't do it. Hydrogen can't do it. Spinning flywheels have their place, but there's engineering scale-up issues there. Compressed air has its place as a storage system, but it has its scale-up issues. You can't actually sort of roll it out at the same level. The problem here is the sheer volume that we need, the quantity of power stored and for how long. That brings us to scenario N. Now, this was has been proposed as a possible solution where we don't need the buffer at all. We will need a 6-hour buffer to do the intermittent day-to-day balancing, as what the Net Zero America project has shown. But if we reduced our passenger car fleet by using automated cars and car sharing, and we had a 3 times build out of wind solar, would it work? Well, let's look at that. Okay. So the passenger car fleet is cut back to 10% of its current size. There'll be automated cars driven by AIs. If you own a car, 90% of the time that car is sitting in a garage being unused. What if we shared them? But that'll only do passenger cars, which is actually a tiny fraction of the whole fleet. So we will now have 1/10 of a fleet, 1/10 the size, but we want the same number of kilometers. So 1/10 of the cars are doing 10 times the work. So what that means is the batteries will last 1/10 the time and they'll have to be replaced. Heavy trucks, buses, and rail and maritime shipping are already optimized and they're flat out. They're not going to be able to be shared as such. Trucks are already running as long as they can, their drivers can tolerate. The power buffer storage is cut back to 6 hours, and it's a battery bank. And the capacity for wind and solar, which represents 76% of the total power grid, is now built out to 3 times the actual capacity, and the power needs outside the transport fleet are the same as in 2018. And this is how it looks. So this yellow band has been multiplied by 3 times, and now we end up with an 123,896 terawatt hours of capacity to be installed. And now we're talking about 2,172,882 extra power stations to be produced, or an installed capacity of 78.8 gigawatts. Now, to put this in context, the power generated in 2018 was 26,652. And the power plant fleet at the moment is about 46,000 units. Now, this is the difference between when you knock out a single coal-fired power station, how many solar panels do you need to replace it? And the installed capacity in 2018 was about 5,000 gigawatts. Right. So now you've got this massive expansion. This is the amount of metal we would need. So these are the metals. This is the quantity of metal in million tons, according to this scenario. This is the global metal production as it was in 2019. And these are the years to produce at current rates. Anything over 27 years is coloured red. Many metals are actually red. Germanium is at 32,000 years. What's happening here is germanium, we produce about 130 to 140 tons a year of germanium, but it's used in one of the solid-state battery chemistries. And solid-state batteries are flagged to take over about 1/3 of the market. But if that's the case, if there are 3 battery chemistries and they take 1/3 of the market, that would then require an increase from about 130 tons a year to 4.16 million tons. Right, so that's, and all the rare earths are all well and truly over the top. Right, so now we've got the problem with the mining industry not being able to deliver in terms of rate. Let's look at reserves. So if we put this amount of metal up against reported mineral reserves, now remember, we've got to do this in 26 years. And since it takes about between 15 and 20 years to open a new mine, going into resources is going to be tough. So let's look at reserves. Anything less than 100% is coloured red. The amount of metal we want, the amount of metal we have in reported reserves. So we still have shortfalls at the mineral reserves level. So basically, even at this scenario N level with a 3 times build out, we don't have enough production and we don't have enough reserves. But will it work? All right, so if you assume that we're producing during the day and you get what you need from the entire day, we have to look at the natural capacity factor. So for solar, the average worldwide is about between 11 and 13%, where it's 11 in Germany, and in the best parts of the world, like California, it's up like 25%. The natural capacity factor for wind is between 21 and 24%, with some parts of the world up to 50%. But in places like Indonesia, it's really low, 10%. Assuming you're 100% efficient in moving power from day to night, you still have to have an overbuild, an average of 4 times overbuild globally. Or if for solar, for example, in Germany, it'd be 9 times, but for some of the wind turbine farms in Germany, it's 2 times. All right, now we're going to assume that the storage medium needed is used and how much loss is there in moving power from day to night. Hydrogen, with its 28% round-trip efficiency, now we've got to multiply the overbuild by 3 to 5 times on top of that. Now, hydrogen is the only scalable problem storage that we've actually got at the moment, but there are practical difficulties. If battery banks are used, which is not actually possible, as is shown, but let's say we force the issue, you lose about 20 to 40% in storing power over such a long time, so we've got to multiply, say 1.5 times again. So now we have an overbuild of 6, 4 to 1.5, to 45, 9 times 5. And so let's say conservative, let's say it's 15 times. So these are our natural capacity factors. So now let's think in terms of overcoming seasonal weather deficiencies. I remember in Queensland, for example, when I was living on Mount Tamborine, every now and then you get these weather events. Like it would rain for 8 weeks without a break. And I had solar panels on the roof at the time, and during that time, it produced no power at all. So 0. 3 times 0 is still 0. So assuming, let's say we only need 10 days of seasonal variation. 10 times 15 is 150 times. On the other hand, let's say 60 days. Remember, this is our power grid and we need the reliability. That's 60 times 15. Now we're at 900 times. So 3 times build out is not nearly enough, even if it was even possible. But will it help? If the sun doesn't shine or the wind doesn't blow in bad weather conditions, which can last for a couple of weeks, will it work? The answer is probably not. So this whole scenario, I would like to see some proper simulations to show me that this would actually work. And so far, it does not. So that brings us to the sensitivity scenario. What I've done here is I've taken my model, and there's 800 and something tables of data, and they're all linked. What I've done is I've changed one parameter at a time and then see how the final outcome is. What happens if we change, for example, the electric vehicle system and we reduced it by 50%? The fleet was reduced by 90%, or we increased it by 200%. The prediction of the World Bank is the transport fleet is to be 2.4 times the existing size in 2050. We're going to expand. What if we increase buses? What if we increase trucks? What if we increase rail? What if maritime shipping was reduced? What if steel production was reduced? And then what if it was increased? If we're going to rebuild society and wipe out fossil fuels and build an entirely new system, we're going to consume a lot of resources, including steel and cement, and so on. And then we get to the coloured ones here are all about how much extra power would be needed, what changes in power generation would be needed if we made these changes. The alpha, beta, gamma series is all about how much metal we would need if we'd made these changes. Right, so let's look at that. Right, so this is percent change from the base level. This is 0, so the 0 level is 48,909 terawatt hours, plus 20% is 58,000, minus 28% is 39,000. Now 39,000 terawatt hours in addition to what we have is enormous, right? So just keep that in mind. All right, so that's A. If we reduce the fleet by 50%, not much. If we reduced it by 90%, so the existing transport fleet was reduced by 90%, we only get a relatively small bump. If the whole thing was increased by 200%, yes, we get a bit of a bump, and we're up around the 10% mark there. If all Class 8 truck semi-trailers, instead of hydrogen fuel cells, were electric vehicles, right? So that's a change in difference in power. If we increase the bus fleet by 300%, 3 times the size, very little change. So that is encouraging to the idea of moving off individual transport and going to more communal transport. If trucks were reduced by 50%, but there were hydrogen fuel cells, if they were increased by 200%, bigger jump. If the rail network was increased by 300%, or now we're into maritime shipping. Maritime shipping moves stuff around the world with things like container shipping and what have you. And if we stop doing that because it consumes a lot of fossil fuels, reduce it by 10%, reduce it by 50%, and reduce it by 90%. Doesn't make that much difference. Steel production, if reduced it by 50% or 90%, or we increase it by 200%, or increased it by 300%. Now, if we're going to rebuild lots of stuff very quickly, we're going to need much more steel, and it's going to be much, much more than 300%. Ammonia production, we're now going to produce lots of ammonia, but we can't use natural gas anymore. All right, we'll reduce by 50%, 90%, but hang on, that's probably going to be our most sensible fuel for the maritime industry. So what if we increased it by 200%? Building heating was reduced by 50%, very little change. Now, what if we reduced conventional electrical power that we use at the moment, and we had efficiency gains and we reduced it by 50% or 90%? Sounds pretty scary, but they're the big changes. What happens if we increase it by 200% or 300%? We're all the way up there. Okay, so this is the amount of power. This is how these things change the amount of power that we need. So EV, this is the electric vehicle fleet, heavy truck changes, rail changes. So the biggest changes are if we change our electrical demand and we change steel production, and after that changes in the trucking fleet. So they're the biggest ticket items if we're going to sort of change things. All right, so now let's look at some of these different ideas where what if solar panels became twice as effective and increased their operating hours by 200%, or wind turbines increased by 200%. So we're not talking about efficiency gains a little bit. We go from, say, wind turbines go from 24.9% to 50%. Right, not a lot. So this is the amount of metal that we would need, and it's changed from zero. What if our energy mix, we wiped everything out, and it was entirely wind and solar, 50% solar PV and 50% wind? That's a big change here, 30% increase. What if the energy mix was altered to include more nuclear? Now, in this mix, I've got 7.5%. So if we increase it to 10%, well, we get a bit of a drop. If we increased it to 20%, a bigger drop again, or if it increased to 30%. So it's a 30% reduction if nuclear actually was increased to 30% of the power grid. Right, so that's our biggest change. One of the predictions for the future is that power generation will be all wind, all solar and all wind. That's up at gamma. And then you will have the idea of what if we had a bigger share of nuclear. That difference in the power energy mix shows the biggest difference. What if 80% of the batteries became LFP? Or what if 80% of the batteries in electric vehicles are solid state? No difference. Now, I also made a hybrid scenario called scenario mu. Now, this was actually to see what if degrowth actually happened? What would that look like? So what was scenario mu? This is all assuming a 28-day buffer, which again, too small. Sorry, it is. Right, so scenario mu, I'm in contact with the Club of Rome, and the Club of Rome is promoting the idea of degrowth to avoid a resource shortfall. So society was to degrow, and we did the following. Our Class 8 HCV semi-trailer trucks fleet was reduced by 50%. Rail was increased by 300%. We're now on communal transport. Buses are increased by 300%. Commercial vans and light trucks are reduced by 40%. Passenger cars are reduced by 70%. We're talking a pretty serious reduction. Motorcycles, 70%. Maritime shipping was cut back by 60%. Steel production was increased by 300% because now we have to make a new society. Conventional electrical power demand was reduced by 50%, and nuclear power now accounts for 20% of the energy power generation mix. Right, that's a pretty savage reduction. That's actually far more serious than it's actually practical. What does it give us? Minus 15%. Minus 15% after all that. Why? This is scenario mu. This is the copper required. 96% is still going into this power buffer. Right, the power buffer again, the sheer size of it. Pumped hydro can't do it. Stored hydrogen can't do it, and battery banks can't do it. We don't have another option. So wind and solar are not viable as our energy source. If we're not allowed to use wind and solar, what exactly are our options? So what does it mean? Current plans for the after oil are just not good enough. Current thinking is seriously underestimated the size of the task. Battery chemistries other than lithium-ion will be looked at. That's interesting. That's still being resisted. The effectiveness of renewable energy systems, we might have to accept the fact that they're not strong enough to replace fossil fuels in their current form. We just need too many of them, and they're just not as effective in operation to replace fossil fuels. Hopes for future technology breakthroughs to somehow deliver more commodity resources don't seem to consider the nature of what's left. in the current system has absolutely no idea of its dependence on minerals and does not consider concepts like continuous growth in production against finite resources. Now, we're getting nasty. Replacing the entire system, wiping out fossil fuels and replacing the whole system, but doing it for 8 billion people, we're probably not going to be able to do that. We don't have enough for the whole human population. There's simply not enough time, not enough resources, and, well, frankly, we don't have the money either. So what will end up happening is whether we do it by choice or whether it will be done to us, a massive reduction in societal demand of resources of all kinds. It implies a very different system of governance, what's happening today, and it leads to the conclusion that the entire green transition is a stepping stone to something else as opposed to the final solution. So we really should give some thought about what that something else might be. Ecological reality and biophysical limitations will reassert themselves. So the system is about to evolve, and we need a better plan. And that plan has to be attached to reality. Or there's been way too much talky and not enough wickety-whack. So what do we do? Now, this is a picture I took at Rainbow Beach. Those are my footprints. I've actually found a series of solutions, but a lot of them are unconventional, and a lot of them are actually not that, it's difficult to talk to people about them because they're often rejected already. I don't care. I'm not here to follow the path of others or actually fit in with what other people think should happen. I'm developing my own path, and I'm blazing a trail out to where there are no other people. The existing system is showing signs of structural stress. The green transition will not work in its current form, but we will attempt to solve the same problems because we must. The circular economy and the steady state economy will need to evolve. They're the only systems that can, and it's up to us to build a new system. We can't wait for someone else to do it. An unprecedented demand of natural resources of all kinds will now be needed. And as Richard Heinberg likes to say, it will be the project of the century once we finally get our arms around what we need to do. Plan for a radical reduction of consumption of natural resources and a new system once established. And the new system requires a new relationship between us, energy, raw materials, and the planetary environment. What do? Restructure society to operate a different energy generation system using unorthodox technology produced from resources extracted to a different business model to what happens now. And after that, you can have the rest of the day off and a nice lie down. We must change our paradigm. We all want the magic bullet to solve things quickly. We don't want to hear about any work to do. We all want a universal solution that involves no effort or change in behavior. And we want someone else to develop the solutions. How often have you heard that the free market will fix it? Or human innovation is amazingly powerful. So is denial, guys. Right. And then once we see the solution, we want to take it. We want to elbow everyone out of the way, take it so we can get rich. Usually we think in terms of patches. We, instead of actually sort of thinking about like a completely new idea, we want to actually take out one part of a system and replace it, and then we go on as normal. For example, take out internal combustion engine vehicles and replace it with an electric vehicle, and the same basic actions will happen and life will go on as before. All existing solutions are based on ideology I've seen so far. There's very little practical thinking has gone into them, and many really look like a Band-Aid on a bullet wound as a direct consequence of that. We must change the rules of what can and cannot be. So I actually got my fingers smacked for this one. I did a report where I actually looked at all different energy systems and all different propulsion systems. And at the time, when I was actually doing this, the White House, the American White House released a report saying what we call UFOs were in fact real, they just didn't know what they were. Management found this and actually sort of quietly suggested I take this out of the report, and they also mentioned my coffee might be rationed. And they told me that I'd gone too far. Then again, never tell an astronaut they've gone too far. Imagine a technology that can do 600 to 700 G forces, that can fly at 13,000 miles an hour, evade radar, and can travel through the air, water, and possibly space, has no visible method of propulsion, no wings, no controlled surfaces, yet can defy the natural effects of Earth's gravity. It's precisely what we're seeing. Now, I don't care if a little green midget with antenna is flying that or a Russian agent. Don't care. Question 1, what propulsion energy technology is this, and what's the energy source it's used? When we say someone is going to think of this because human innovation is amazing, someone better get off their ass and do something useful, or we're back to we all freeze to death in the dark. This is a very controversial thing to say, but it does suggest that not all options are on the table and innovation thinking is actually still possible. What do? Come back to energy in a moment. How do we reorganize a society? We've got to decouple from some systems, develop new systems, and socially evolve to not need others. Energy systems technology will go first. That's what we need to sort out first. Industrial systems next. How do we use that energy? And that's a source vector of energy and a source vector for raw materials. They have to be coupled at the same time. Then we'll look at how do we distribute our human population? Do we still stay in large cities? Food production, management of arable land, and the management of phosphorus and nitrogen cycles. That's code for industrial agriculture will have to be phased out and replaced with something else. Fresh water, transport technology of heavy goods and raw materials. All of this will have to be viable, but we'll probably organize things in this order. Now, we're probably going to do this in this order as well. This is the amount of power we need, and then this is the total metal. Is the question, do we actually need all this stuff, or can we evolve where we do something else? Now, because we're out of time and money, we've got a metal shortfall, we're going to look at degrowth very quickly, whether we do it on purpose or it's done to us. First thing we're going to do is look at things like alternative chemistries that can be sourced from different raw materials. So what we mine changes. And when that doesn't work, we'll then go to, well, can we look at different technologies instead of an internal combustion engine, and we're going to look at an electric vehicle or something else. Then again, when that doesn't work, we're going to think about ripping out the whole system and making a new one. The questions now is, what is the energy intensity needed? What are the raw materials needed? And what logistical supply chain is needed? Tasks to be done. Conduct a Maslow hierarchy of needs analysis loop in context of industrial activity. So instead of doing this for a single person, we will now do it for, say, an industrial system. Electrical power generation. What is the hierarchy of needs, and in what order do we need to see them? Do that for each of our systems and then rank them in a hierarchy in its own right. Conduct that analysis and keep going till it stabilizes. Reorganize the industrial value chain around a low energy future and a very short supply chain that is inconsistent in performance. Retool the existing power grid into a series of microgrids, where each microgrid is attached to a use, for example, a smelter, a mine, a hospital, whatever. And each microgrid can transfer power between them, or they can shut down without damaging other power grids. Develop an engineering technology that can cope with variable power supply, power spikes. If we can do that, we don't need the buffer, and a lot of our problems go away. Plan for a reprioritization of industrial capacity. Different things will become valuable. Plan for a systemic merging of energy and raw material feedstock to all industrial actions. They're no longer just costs of doing business, they now are rate determining steps. The mining industry in all forms is right in the very heart of this. Plan for an economy where industrial capability can periodically shut down. For example, a period of dormancy over winter. Develop an engineering decision-making system that can define whether something is logistically sensible or economically viable to a new set of constraints, for example, exergy. And develop the ability to find substitutions when things go wrong. Evaluate what's really needed and plan to do it in a regional scope instead of a global one. This is not rocket science. Make batteries out of something else. Now, down the bottom, this is theoretical gravimetrical energy density versus theoretical volumetric energy density. These are the atomic isotopes compared against each other. Lithium-ion batteries is in the bottom left-hand corner. This is theoretical. What actually is on the market is actually lower again. There are other chemistries. Sodium, we're now starting to talk about that, but no one yet is talking about fluoride batteries or magnesium batteries. So I'm in battery chemistry research projects. They are still resisting going past lithium ion because that's what the industry wants at the moment. The minerals we now want are things like zinc and fluoride and sodium and magnesium. So these are the sorts of things that are found in industrial waste. Oh my stars and garters, this is a circular economy action. So the valuable part becomes processing and refining into something useful rather than the resources themselves. Now, it's not rocket science, but we've actually got to get in there and actually do it. And at the moment, we're not even doing that. The commodities industry has been misunderstood. When we talk about commodities, usually we talk about like finance and economics, sometimes about technology. When you see on the news, it's all about the stock market. What's really happening is this. You've got minerals, economics, technology, and energy. They're all joined at the hip. When you see one, you've got the other three, and there's not a lot you can do about that. So any real system, and we're also harvesting, all those aspects are harvesting out of the natural environment. So this is how we're really structured, but we haven't been thinking in those terms. But any new system will have to have a similar structure that will honor these things. Our relationship between all four aspects in the planetary environment is changing. The situation we find ourselves in at the moment is two inverted pyramids. We used to have energy reserves of oil that were massive and really high quality. So high quality that you didn't have to do a lot to get hold of them. Now we've got these massive low quality reserves like Canadian tar sands that we've got to do a lot of industrial actions to get hold of. Mining, on the other hand, there was a time when we were really, really small deposits. That's actually a natural copper nugget. Chris Martinson first posted this picture in 2008, and I've been using it ever since. So that's actually a nugget found in the streams in North America when European settlers first arrived there. But now we've got these massive low-grade pits, and cut-off grades of 0.1% are now being considered. So the energy system needs to replace with something high density, or we've got to let go of how our society is structured at the moment. We also need to replace, or if we can, where we're getting our raw materials. Like, can we rethink that? Can we think of an alternative? So back to energy. Each energy sector I've looked at has a bottleneck and scale up. We've actually got to do something. One of those sectors has to evolve. The most sensible one I found so far is actually something from 50 years ago. So this is an evolution of the nuclear industry, where this is actually liquid fuel fission, where at the moment standard practice is what's called solid fuel fission. Liquid fuel fission works very differently. And if we use thorium as the feed, the footprint is very different. So this is actually a report from 1972. 1972 from the Oakland Ridge Laboratory. It's a report outcome of several $1 billion in research, and it's a status update. So what you're looking at here is thorium salt is put into a reactor, it's bombarded with neutrons till part of it actually sort of goes to an isotope of uranium-233. That heats up because it's radioactive. The salt melts and it becomes a fluid, and it moves around the system and it exchanges heat. That heat is then used to generate electricity. We don't need water to cool this down. Right. So this was the Oak Ridge reactor, a little under 8 megawatts of installed capacity. It ran for 6,000 hours without an incident. The Chinese now have a system up and running in the Gobi Desert. It's 2 megawatt hours. It fits in a shipping container, as you can see, and it's commercially selling power. So this is not a theory anymore. It's actually a viable option. There's also a group called Copenhagen Atomic that are actually planning to be selling these things as soon as in a few years' time. They will have a demonstration unit up and running, generating power in 2025. So this actually may well be a viable vector out of this. Okay, why do we care? Let's look at the difference between, let's look at the conventional uranium light water reactor. This technology was developed in the 50s. We want to generate 10,000 gigawatt hours a year out of one reactor. You start with 123 million tons of uranium ore, and we make 278 tons of yellow cake. Convert it and enrich it. We want to enrich the uranium-235 to about 4 or 5%. From its natural 0.7%. We then end up with 32.9 tons of nuclear fuel rod assemblies, uranium dioxide. Put that in your reactor. And when it can't sustain the reactor anymore, we take it out, and 96% is waste. Uranium-238, very radioactive and nasty. About 300 tonnes has to be stored for 3,000 years. 19 tonnes has to be stored for 100,000 years. That's out of a single reactor for 1 year. Now let's do the same thing with thorium, liquid thorium. Take 280 tonnes of mineral sands. So already we're going from 123 million tonnes just to 280. So it's a much smaller system already. 1.45 tonnes of thorium dioxide. We're going to make 1.34 tonnes of thorium salt, put that in the reactor, generate our power, and about 4 to 5% is not burned through. So you end up with about 50 to 60 kilograms of radioactive waste that has to be dealt with. The isotopes are the same as what we use in the medical industry. And so they could either be recycled into the medical industry or stored for 300 years, not 100,000. So the footprint of the thorium system is much, much less, and it's also not radioactive until we get to the end, whereas uranium is reactive at every step, and we need specialist training at a much higher level. So I do think that we actually, this is actually a useful thing to look at. So in practical terms, other nations like China, United States, India, Sweden, they're all pursuing this already, and everyone else will have to be their customer or they get left behind. Right. Now, the mineral system, we now need to actually look at what are we actually doing? And so mining is only part of the cycle, but we need to map the whole thing. And so this is the idea of mineral intelligence. And so we need to get hold of this somehow. And so I've come up with 5 basic ideas. So we need a material tracking system that can actually go through the whole value chain. So we're talking about some kind of auditing system, blockchain or some other tool that's like it. An engineering mapping of how each material relates to the whole ecosystem. We need a data information management system to make engineering decisions in a timely fashion. We need to be able to characterize material flows fast enough to be useful. And we need a technology evolution of industrial systems as new tech requires new minerals and new metrics. So we have a system like this. And so we've got raw materials. How do we go from a raw material to a refined metal or a chemical? How do we take that refined metal and turn it into something like a computer or a car? How does society use that car or computer? And as things become obsolete or come online, how do we manage that? And in between, we've got a management system. So we have to develop an information management system that allows us to make intelligent choices fast enough. So what technology is produced from what raw materials? How is that tech used? How do we manage those new systems coming in? And how do we keep track of what's going where? And how do we make decisions fast enough to be useful? That's our target. So we have a whole series of these maps. How do we go from an exploration system all the way out to a bar of 99.7% copper metal? And we've got all these steps in between. So we take that and put into something like the HSC simulation software and actually do a thermochemical calculation where each step along the way can be mass balanced and mineral balanced. What went where and how. So then we do that for each pure metal. Then we go, so well, how do we use that? So this is a wind turbine. It's made up of metals. So such simulation would have to be made for each metal and each construction step. So it's getting a big job. So let's say we've got our wind turbine. How do we use our wind turbine? It goes into a bigger system. And then how does it work? How long does it last? Life cycle analysis. So we need to do this for all industrial actions. We're talking about a massive information system. This is the idea of digital twins. It's also the foundation of things like mineral intelligence. So what we call the circular economy has to evolve. The Swedish government challenged me and they said, all right, smart guy, you scared us, but now you're going to fix it. They wanted me to write a document and they had the challenge, it had to be 50 pages or less, of how could the circular economy evolve in context of my work? And so I've put forward this idea of the resource balanced economy. And so this is actually that policy briefing, and that's actually here. So the resource balanced economy goals and tasks, We want a new system of governance, a new energy system, a new relationship with raw materials, including its source, a new social contract, and a new relationship with the environment, and a new monetary system, and a new manufacturing system. These are strategic goals. How do we do it? Well, resource accounting, embodied energy versus strategically useful outcomes, management of dynamic equilibrium, strategic design. What we're talking about there is we design things where they can be recycled easily, and we can design them from commodities that we're stripping out of the environment locally. Statistical entropy matched with material flow analysis of each resource. I'm talking about exergy and emergy. Biophysical signatures and limitations, technology application, evolution, devolution over time. So these are tactical tasks. Once we've got a strategic direction to go in, these are the sorts of things we might be able to get there. So conclusions, this is a skip across the top. Of course, many of these things could be expanded out. The planned green transition is not feasible in its current size and task. Mining, production, reserves, and resources are all facing shortfalls. The needed power storage buffer to manage intermittent supply for wind and solar systems has been overlooked in its current blind spot in the phasing out of fossil fuels. And until the issues raised are resolved, wind and solar are not viable as the primary energy generation system for the next industrial era. What energy systems we use to phase out fossil fuels has yet to be determined. It will need to be high density to maintain existing society metrics. There are solutions if we choose to see them. Restructuring society will be needed in any scenario going forward as a consequence of having a different energy generation system. Degrowth in a hard landing will be inevitable by virtue of leaving these issues to the last possible moment before acknowledging, let alone doing credible solutions. Thank you, and huzzah. All right, are you still there?
Yes,
Hello.
we are still here. Thank you, Simon, for a very interesting and thought-provoking presentation. And also thanks for presenting. I think it's now just past 2 a.m. your local time.
It is indeed 2 a.m.
So we've got quite a few questions. I'm just conscious of the time. Did you want to answer a few of these?
Yeah, we can do that. Look, I'm in no danger of going to bed. When I'm done here, I'm actually going to get back to work. So we can
cool.
take these questions.
Cool. So we've got the first question online from Janine Herzig. So I'll just read these out so everyone online can hear them as well. So why are governments and other decision makers so ready to accept assumptions with no basis in science or reality, for example, emotions or desires? Yet when presented with factual, scientific and engineering-based research, they are quick to dismiss it as being unproven or too late, too hard or too expensive. The proponents of hydrogen and undersea mining pick and choose the facts to prosecute their own interests and arguments.
Right. So this is the 199th time I've presented this work in various forms. About 30% of the time I'm presenting to government. Right. And so what I'm finding is they're not rejecting these ideas, right? But they are shocked. They're shocked and they can't refute the numbers even when they're given time to do so. But in every single case so far, they've asked me what they should do. Now, I'm just a guy with a cheap computer and an internet connection. They've got the resources of a government department backing them, and they're asking me. And what that has shown me over time is everyone I've talked to is trapped in a system where they've got relatively little latitude of innovation. They just don't know what to do, and the solutions that are necessary mean that their existing jobs may not exist, or they've got to cede power and step down and hand over to a new system. And they just don't know what to do about that. It's not that they're rejecting these ideas, they just don't know what to do. For now, for the last 50 years, we've been doing our problem solving on what you might call ideology. Because the system's been so strong, energy's been so abundant, money's been so easy to come by, and resources have been considered to be unlimited, it's been okay to think in these terms. And it's not until we're actually hitting these kind of resource limitations that we have to actually consider things like how much. So we're being asked questions for the first time in our industrial civilization, and people aren't prepared. That's the simple answer.
All right. The next question. So clearly there's a big disparity between identified resources and reserves and your projected demand. However, at least for some metals on the list, there has been significant historic production. Have your calculations factored in any recycling at all for those metals that are already extracted?
So I did look at a little recycling. I'm looking at a piece of work with Marcus Reuter that's actually looking at the idea of the quality of metals and the embodied statistical entropy of recycling. And because we're not designing things to be recycled, our recycling rates are really, really poor. Now, most of the metals that we're trying to chase for the green transition are exotic. We do use them now, but in relatively small amounts. Cobalt and lithium, for example, are used in relatively small amounts, but now we want to mine them and use them like copper and steel. So far, historically, yes, we have used a lot of these metals before, but not nearly enough. So the metal we've mined to date is a tiny fraction of what we need going forward, and there is not enough metal to recycle that's already been mined historically. The stuff like copper, that's actually going to be the one that's going to be the very difficult one to overcome. We can make batteries out of something else, but good luck replacing copper and nickel. The simple answer is I have not done a recycling study to the point where, or to the same level of sophistication. It does need to be done, but some back of a napkin results show so far that recycling, we just don't have enough in the system already, and it's not nearly as effective. Even if we can solve the collection problem, which is a can of worms in its own right, the quality of the material flows that are coming out of recycling is just not good enough.
All right, we have another question from Janine. So she says, I saw you in Canberra back in September and know you were paraded in front of some politicians. The question, did you feel like any of them were actually listening or understanding what you were saying?
So I just did a tour, right? I went from Switzerland to Canberra to Hong Kong to Florida. When I was in Canberra, there was a palpable feeling of anxiety, and I actually sort of spoke to a number of the different political factions, and I presented to ministers inside Parliament House, which was cool, and ministers and their aides. And what we had around the table were people who were from different parties, but Canberra politically has committed to the idea of a green transition where wind and solar is the primary way forward, and they've more or less committed to that. And my information was showing that that's probably not going to work the way they think it is. My work was actually put into a form that could be shared, and it was sent down to every senator and every aide through the whole system, and they all looked at it. So they understood what I was looking at. They did have a bit of pushback in terms of what do we do. Once they actually sort of checked some of the information themselves, they did come to the conclusion that what I was presenting to them was conceptually correct in terms of, like, I asked them how many cars they thought there were in the system, and they didn't know, and they checked it out. And they thought, oh, okay, it is a couple of, it is more than a billion. And so where are we going to get that stuff from? They immediately went to who's going to pay for this stuff. And so they went to parts of the analysis that haven't been done. Who's going to pay for this stuff? Where is this material going to come from? For example, manufacturing in, say, China. Is manufacturing in China enough to supply the volumes? No. And so they asked some hard questions, and they came to the conclusion, well, we've got to do something. And then the meetings all ended, and I didn't hear how it went from that. So it was actually more, I was expecting more platitudes and it's a river in Egypt, but it turned out they actually did take it seriously, but they just, again, don't know what to do.
All right. The next question is from Malcolm Powell. So, hello, Simon. Nice review of reality. I note pumped hydro does not need new water consumption as it is recycled through the system. It does need larger reserves and there will be losses. So I think topping up the reserves is the actual need for water, and pumped storage is still huge. And then sort of a follow-up question still on the same pumped storage is, have you modelled hydropower for energy storage with the water in a closed loop?
G'day, Malcolm. I miss you, mate. So pumped hydro was interesting. The problem here is the sheer quantity of power we need to store. If we're talking about a relatively small amount of power, then you can have a closed system. If we've got a large amount of water, storing that system is going to be a problem. Having that water go into a reservoir and out again, it's going to be discharged back into a river. So if we do actually store it, right, now the sheer amount of water we're talking about is huge. And if we use it, for example, if we drink it, we're consuming the water. So the consumption of water versus storage of water versus where do we put it and how do we do it? The study I did was fairly primitive, and it probably does need finessing. But the idea, it very quickly became apparent that a closed loop wasn't going to work with such a large volume of water that was needed.
All right. Another question from Mark Noppy. So, hi, Simon. Thank you very much for the compressed, comprehensive summary of the issues. Your conclusions resonate. I dialed in late, but did not hear you discuss nuclear energy as more than a 20% supply scenario or Club of Rome scenario. Outside of your proposed paradigm shift, what could greater nuclear energy provide to meet the gap?
So, g'day, Mark. I did do a sensitivity analysis, and I looked at what would happen if nuclear actually did take a larger cut. I looked at 10%, 20%, and 30%. And with each additional amount of nuclear power, there was a substantial reduction in the amount of metals that would be needed. So yes, it would work, but then you've got the problem of expanding the nuclear power plant fleet to reach that cut. And that's where the trouble starts, because you've got to build those nuclear power plants, and we can only build them so fast. Then there is the infrastructure needed to handle the nuclear waste coming out the other end. I think an evolution of nuclear is actually probably more sensible rather than trying to force the issue with the existing nuclear technology.
So then following up from that, Tim Napier-Munn has a question. So is thorium-based nuclear the final solution?
There is no final solution. Hello, Tim. I've been telling people about you here in Finland, by the way. So if you get some calls from Finnish-speaking people asking about statistics, it'll be my fault. So thorium energy looks like it could be useful. Is it the final solution? I think it's a stepping stone to something else long-term, but it could well be a foundation energy system if it proves to work like the Chinese government's claiming it's working and how my colleagues at Atomic Copenhagen are claiming it's working. If we can actually do that, then we've got the problem is, can we scale it up fast enough to be useful? And there are some unanswered questions in there. I'm reluctant to say things like final solution, but it's the most promising solution I've seen so far. That's probably a better way to put it.
All right. The next question is from Jim Morrison. Have you looked at the cost of doing nothing and how it compares with the net zero cost?
No, I didn't. In other work, I've done things like a do nothing scenario. Like I'm doing a job in Hawaii at the moment is what would happen if Hawaii had to phase out all fossil fuels. And one of the scenarios is do nothing. In this work, I didn't. The purpose of the work in the first place was the flamboyant promises being made by European Commission senior officials and what they thought the future was going to be. So I was trying to actually map what they thought they were going to be and show how it's not going to work and we need to go back to the drawing board. Doing nothing, that is a piece of work which would show that doing nothing is not an option, but I haven't actually done that work.
All right, then another question from Andy Reynolds. Where are your strongest allies?
It's an interesting question because I keep being asked back by people in senior positions in all sectors, government, capital investment, banking. I'm getting allies all over the place. No one challenges me to my face. My critics are usually armchair warriors on Twitter. Instead of allies, I'd say the most useful people I've come across so far are actually postgraduate students, people who've just finished a master's degree and have moved into the workforce, or people who've got a master's degree and are now doing a PhD. Those people will be in positions of responsibility in 10 years' time. So those people will actually be making the choices needed, whether we get through this or not. Now, they're not in the workforce yet, so they're not as cynical as people like me, I suppose. but they seem to be easier. They could handle these things easier and get their arms around the issues faster than any other group I've seen so far. Allies, they're everywhere. They're all around us, and they're of people of every stripe, as are the adversaries. There doesn't seem to be a pattern that defines them.
All right. And then the final online question that we had was from Shailendra Gautam. Thanks, Simon. What will happen to existing fossil fuel resources and businesses who will keep exploring more and more?
The sad reality is the vast majority of the system is still fossil fuels, and it will take us time to build whatever the next system actually is. So fossil fuels, all three of them, will continue to be used for some time yet, and we will be dependent on them. For example, if we took away coal, most manufacturing actions would stop. We don't have an option. To make a solar panel, you've got to get a silicon wafer, you've got to get metallurgical silicon, you've got to heat it to 2,200 degrees Celsius. It's done in China, and they use coking coal to do it. Take away the coal, how do we generate that heat with renewable systems? The answers are some forms of biofuel, some hydrogen applications, and some applications can be done directly with electric arc, but the quantities involved are so large that we actually can't deliver those systems yet. So when we knock out fossil fuels at the moment, we have no alternative. And even though at this very late stage of the game, we're only starting to look at this only just now, the vast majority of the system is still fossil fuel dependent. So it's going to be business as usual for some time until it crashes.
All right. And there was one more online question which came in. So you mentioned biophysical constraints, but there's been no mention of biological constraints. It's known that mining will destroy ecosystems and biodiversity, and we're talking about a massive expansion of mining. This will have independent climate effects. Could you please comment on this?
Guys, you only gave me an hour. Come on. Right. So that is indeed correct. I have actually looked at some of the ecological impacts of mining. There is actually a piece of work to be done on that. I was going to be collaborating with various groups to look at that. The simple answer is, if we were to expand mining production at these rates, the environmental impact would become unmanageable. It is very clear that is the case, but it's also, the work hasn't been done to the point where we can actually put some numbers to it. The work I've done so far has been around the food production, use of fertilizers and industrial petrochemicals, and it really does show that there is a fairly serious problem that we've got to manage.
All right. Well, I think that's all we have time for now. So please join me in thanking Simon for his presentation this morning.